Ladies and gentlemen, Bell Laboratories invites you to hear the light. Hello, I'm Henry Feinberg at Bell Laboratories, and what you just saw was my way of changing sound into light. And that's what we'll be talking about today. We'll investigate some of the characteristics of light, and we'll see how the Bell system is using them for telecommunications. Our new system is called Light Wave Communications, and Bell Laboratories, with the cooperation of Western Electric and the Illinois Bell Telephone Company, has installed a working light wave communication system beneath the streets of Chicago. It's a full-service system carrying voices, computer data, and also video signals from picture phone meeting service. Well, the idea of using light as a communications medium may seem like a very new concept, but really it's not new at all. It's quite old, as a matter of fact. It's very old. It's as old as signal fires. It's as old as smoke signals. It's as old as one if by land and two if by sea. And it's even as old as Morse code blinking from ship to ship. In fact, the idea is so old that back in 1880, only 4 years after Alexander Graham Bell invented the telephone, he invented the photophone to send his voice on a beam of light. Ahead of his time? I think you'll be surprised at how far ahead of his time Mr. Bell was. Here's a drawing of Bell's photophone. Now, the most powerful source of light that Bell had to use was, of course, the sun. So he reflected sunlight from a mirror through lenses to form a beam of light. The beam hit the silvered surface of a membrane stretched across the end of a speaking tube. When Bell spoke into the tube, his voice vibrations vibrated the membrane and imparted those vibrations to the beam of light, which went on. Well, that process is called modulating the beam of light. I built my own modulator, light modulator, out of this glass funnel, which I've covered the face of with silvered plastic. And I have a speaking tube, a piece of hose, that I'll place on top of the projector here, my light source, and I'll reflect the projected light onto the background. When I speak into the speaking tube, we can see how my voice vibrations are vibrating the light. Well, this is really not a perfect working system, but it gives you the idea of how my voice can modulate a beam of light. Well, Bell had an idea that if he was able to put his voice onto a beam of light, he should also be able to find a way of taking his voice off of the beam of light and converting the light back into sound. And he tried various methods with very little success until he came to the idea of using selenium. Now, the idea, selenium is one of a class of elements that is neither a good conductor of electricity, but it's not a very good insulator either. It's sort of halfway in between. We call these elements semiconductors. The property of selenium that intrigued Bell was that when exposed to light, the conductivity of selenium increases. It allows more current to pass through. We can see that with this selenium photodetector that I have here. And I'll connect it in series with a meter, and I'll connect the meter in series with the selenium photodetector and a battery. And we can see that the current is passing through the meter. When I place my hand in front of the selenium photodetector, we can see that less current can pass through it, and the meter goes down. It drops. Well, here's how Bell used the selenium photodetector to receive the light. This is a drawing of Bell's photophone receiver. Here he has a parabolic reflector. The purpose is to concentrate the incoming rays of light to the focal point, and that's where he put his photodetector. Also, he placed his photodetector in series with batteries, the same way we did, but instead of using a meter, he used a pair of telephone handsets to convert the varying current back into sound. Well, he did it 100 years ago. Let's do the same thing today. For our light source, we won't use the sun, but we'll use this flashlight. And as the modulator, I'll use this cardboard tube, which I've cut at an angle, and I've cemented a piece of silvered plastic to the top. I'll place that on top of the flashlight and disconnect the meter and turn an amplifier on. I have the photodetector connected to an amplifier, and I'll aim it toward my flashlight. And when I talk into the top, you can hear my voice being sent over a beam of light. It's a very crude system, and I think you'll agree it's not high fidelity, but the thing works. And with his system, Bell was able to transmit his voice over a beam of light over a mile away. Well, we might say, and excuse the pun, that because of Bell's dependence on clear, sunny days, his was a bellwether system. But seriously, it took almost 100 years for scientists to come up with a better set of components. Well, since that time, we've found many more uses for semiconductors, perhaps the most famous of which is the transistor, invented in 1947 at Bell Laboratories. Today, transistors and integrated circuits are made using the semiconductor silicon. Now, one of the properties of silicon is that when properly treated and exposed to light, silicon actually produces electricity. In 1954, scientists at Bell Laboratories made silicon devices efficient enough to be called solar batteries. I have 3 solar batteries, or solar cells, here on this box. They're connected inside to a motor, and when I place them on top of the light source, we can see that they produce enough electricity to turn the motor. Today, silicon solar cells are finding many uses on Earth, but they're also finding uses in outer space, where silicon solar cells power the satellites that are circling the Earth and also the satellites that are going out into deep outer space. Well, let's get back down to Earth right now as we find out some more things about light. Well, one of the things that we know about light is that light is highly unordered, white light coming from this projector. It's vibrating in all directions, or polarizations. We can start to put some order into light by polarizing the light with a polarizing filter. I have such a filter here, which I'll place on top of the projector. We might think of a polarizing filter as sort of a micro-miniature Venetian blinds. And you can see how it works when I put a second polarizing filter on top of the first. I'll turn the lights down so we can see how this works. Now, when I turn the second filter, just the second one, we can see how the 2 crossed polarizers block out almost all of the light. Well, scientists use polarized light to investigate what happens to light when it passes through certain materials. One of those materials that it's interesting to show is mica. Mica is a mineral that when placed in polarized light, well, it's normally clear, but when I cover the mica with this second sheet of polarizing material, and they're between the two, we can see the colors appear. This is because the polarized light passing through the mica is altered, and white light contains all of the frequencies and all of the colors. But in their passage through the mica, some of the frequencies are canceled out, and we see the colors that are left. Well, how do we know that white light has all of the colors of the rainbow in it? We can dissect light. And we'll dissect light not with a scalpel, but with this glass prism, a triangular-shaped glass prism. To do that, I'll put another slide on top of the projector, and I'll turn it on. I'll turn my lights down, and since we're going to bend the light, I'll pull this image down below the screen, because the white light traveling through the prism is bent, but bent by different amounts by the different frequencies of light, or different wavelengths, which we see as different colors. And projected on the screen, we see the visible spectrum of light, going from deep red at one end all the way through the spectrum into deep violet. Well, there's a lot more light outside this visible spectrum that humans can't see. The visible spectrum is only part of an even larger spectrum of energy called the electromagnetic spectrum. Now, the electromagnetic spectrum consists of waves starting at the low-frequency end of low-frequency radio broadcast, TV, radar, then into the infrared, past the visible light that we just saw, to ultraviolet, X-rays, gamma rays, and cosmic rays. Well, let's take a look right here above the visible range into the ultraviolet. Now, our eyes can't see ultraviolet light directly, but we can see the effect that ultraviolet light has on certain materials. I'll turn my lights down and turn my ultraviolet light on, and we can see one of these materials. It's the ultraviolet makeup that I'm wearing on my face. This is an effect called fluorescence, and the phosphors in the makeup on my face are similar to the phosphors on the inside of your screens of your television sets, and also coated on the inside of fluorescent lamps. Well, let's do a different experiment with a different phosphor, and for this I'll need a volunteer. Dawn, would you come up, please? Thank you. It's Dawn Franklin. Dawn, I'm going to take your picture.
Okay.
Okay? And to do this, I'll lower my screen, and I'd like you to stand in front of the screen while I get my camera. Okay, stand to the side, and I'll take your picture. Let me turn the lights down a little bit, and I'll take your picture. Okay, Dawn, would you step away from the screen, please? Well, shades of Peter Pan. Let me turn the lights on, and we'll see why we see your shadow remaining on the screen, okay? Thank you very much, Dawn, and I'll give your picture to you at the end of the show. Okay, thank you. Well, this screen is coated with a phosphor, a different type of phosphor that absorbs light and stores the energy for a while before each of the atoms releases the energy at random intervals. Well, scientists theorize that if they could find a material to store energy and then a way of causing or stimulating the atoms to release their energy all at once, they can get a powerful burst of light. And that's the principle of the laser, conceived at Bell Laboratories by two scientists in 1958. In fact, the word laser means light amplification by stimulated emission of radiation. I have a low-power continuous wave laser here, which we'll use in just a little while. You know, Bell's Photophone used a method of varying the amount of light in step with his voice. The Bell system's new light wave communication system uses a different method. It's called a digital method, by which light is pulsed on and off very rapidly. Well, scientists at Bell Laboratories wanted to find out, well, just how fast can light be pulsed on and off? And I have a photograph that they took of a pulse of laser light passing through a small glass bottle like this. The bottle was filled with a special liquid which made the pulse of light visible. I'll put the picture on the projector, but I have to put the screen up first. Okay, here is that picture. Turn it on and turn my lights down. The photo you see has the pulse of laser light right here in the center. Now, light is traveling through the liquid in this glass bottle at a speed of about 140,000 miles per second. This pulse of light lasts 20 picoseconds, or 20 trillionths of a second, enough time for this pulse of light to travel only about 10 millimeters, or half an inch. Now that is fast. Our light wave communication system uses lasers for lasers pulsing on and off, but not really that fast. I have some of those lasers right here. Let me turn my lights back up, and I'll show them to you. They're very small lasers. They don't pulse on and off nearly that fast. They only pulse on and off about 44 million times per second. I have them here. I'll put them on top of the projector, and we'll try to project them on the screen. Now, it's going to be difficult. I'll turn the lights back down. It's difficult to see these because each of these semiconductor lasers are smaller than a grain of salt. Well, there's a reason why they're that small. First of all, they're that small so that they can effectively couple their light energy into the very thin light guides, which we'll see in just a minute. They're also that small so that they can operate on very low voltages, the same low voltages that power the rest of transistorized equipment. and they're also that small so that they have a very long lifetime. Their projected average lifetime is expected to be over 100 years. And if you don't believe me, I invite you to wait. Another light source that's being used in our light wave communication systems is the light-emitting diode. I have a sample of one right here. This is similar to the light-emitting diodes that we have in our digital watches and also in our pocket calculators. Also, light-emitting diodes today are providing light for the dials of the new trimline touch-tone telephones. The light-emitting diode is a second cousin to the laser, by the way. And just for a size comparison, this is an antacid tablet that I just keep handy in case my next experiment doesn't work. Well, sending a beam of light through the air the way Mr. Bell did is a very inefficient way of getting it from one place to another. Too many things can get in the way. Fog, snow, rain, trees growing up in the way. It's just too risky. There's a better way. It's called light guides. Now, it took the very latest in science and technology to make efficient light guides, but the principle of the light guide is very old, even older than Bell's photophone. Let's do a demonstration performed in Bell's time to illustrate how a light guide works. And for this, I'd like another volunteer, please. Here's Walt Lyman from Illinois Bell. Thank you very much for helping out today, Walt. Would you step around this side? And I'll have to place this apron on you because we're going to be doing this demonstration with water. Why don't you come over here and I'll put this apron right around you.
What does that say there?
It says, "For this I spent 4 years in college?" Question mark? Well, actually, you're going to be performing a very vital service. Step right around here, and I'll bring this stand up so that we can all see. This is a 1-gallon paint can, and it's full of water. The top of the stand is magnetized, so it'll hold the paint can without danger of tipping, and I'll just top off the can. Now, inside the can is a bulb, a very low voltage light bulb. I'll turn my lights down so that we can see it. And I'll put my hand on top, and I think you can see the light inside the can. It's low voltage, and it runs off of a little 6-volt battery, so there's no danger of getting a shock. In front of the can is a small hole with a cork in it. I'd like you to come over here and hold this beaker in front of the can because I'm going to pull the cork out and the stream of water will come out, and I'd like you to hold it so that it catches the stream of water, okay?
Okay.
Here goes. All right. Now, we can see that the light inside of the can gets trapped inside of the stream of water and travels to the end of the stream where it breaks up on the side of the beaker. And that is the principle of the light guide. Very simple. You know, if we were able to freeze the stream of water, we could make a light guide that we can use. Well, I won't wait until the beaker fills up like I can. And the big part of this trick is to get the cork back into the hole. Let me turn the light back on so that we can do that and see what kind of a team we make. Here goes.
Pretty good.
Okay, that's fantastic. Well, thank you very much, Walt. I'll bring this down so that we don't tip it over later and turn the light out. Let me take the apron from you.
All right.
And thank you very much for your help.
You're welcome.
Well, that is the principle of the light guide, and it's a very simple one. Now, luckily, we have a material that's transparent, that's a solid at room temperature, and of course, I'm talking about glass. Light guides, I have a sample of a glass light guide here. It's a thin fiber of glass. Now, this is made of some of the most transparent glass ever produced. They say that if the water of the ocean were as transparent as the glass in this light guide, we'd be able to see the bottom of the deepest part of the ocean from the surface. Now, that is transparent. Well, because this glass light guide is so thin, it will be difficult to see light traveling through it. So for demonstration purposes, let's use this low-powered laser and a much thicker light guide made out of plastic. I'll turn the laser on, put the light guide into the front of the laser, and turn my lights down. And you can see how the light goes in one end of the light guide, gets trapped inside the coil of wire, and can't get out until it reaches the other end. Now, you can't see this on your TV screens, but here in the studio, we can see that the entire coil of light guide is glowing very dimly. All of the light that is coming out of the sides of the coil would be wasted for use in a communication system. To see what happens inside of a light guide, let's use a larger, a much thicker tube. This is a glass tube which I filled with water. And I'll turn my lights down a little more so that we can see this. Now, the laser, light from the laser is streaming into the bottom of the tube. When I start to tilt the tube, we can see the laser light hitting the side of the tube. But instead of bouncing out, it's reflected back into the tube. This is called total internal reflection. And you can see it zigzagging back and forth inside of the tube. Well, actually, this light is not being totally internally reflected, or you wouldn't see any. I put a drop of milk in the water so that some of the light is reflected toward our eyes. Well, it took the very latest in technology and a lot of work to make efficient light guides. The light guides that are used in our light wave communication system consist of a central core of the ultra-transparent glass we spoke of earlier. The composition of this glass changes gradually away from the center so that any rays of light that start to move off-center are bent gently back so that they stay in the center. They never even touch the outer wall of the central core. There's, around the central core is a cladding of a different type of glass, and around that a protective layer of plastic to prevent abrasions. The use of glass light guides in our light wave communication system is even more efficient than using copper wires. In fact, using a digital copper wire transmission system, it will be necessary to have an amplifier, or we call them repeaters, every mile along the way. Using light guides or glass light guides, we only need repeaters every 4 miles. And most telephone buildings in cities where these systems are being used, have telephone buildings located less than 4 miles apart. In our system, we take 12 glass fibers and place them side by side in a ribbon. I'll place this ribbon on top of the projector stage so that we can see the 12 glass fibers. Now, by electrically bundling telephone calls together, we can place over 600 simultaneous phone calls on each pair of light guide strands. So we can place 12 of these ribbons into a protective outer covering like this, making a light guide cable of up to 144 fibers. Now, using 600 for each light guide, or each pair of light guides, this half-inch light guide cable can carry over 48,000 simultaneous telephone calls. Let's contrast this with a digital system using copper wires. To carry 48,000 simultaneous telephone calls, it would take 2 of these 1,800 pair copper wire cables. That's 7,200 wires compared to 144 light guide cables. It gets pretty crowded under those city streets, and light guide communications will help. Well, now that we've found out about light guide communications, or light wave communications, let's put together a working light wave communications link. For the transmitter, we'll use this small box that has a circuit inside which produces pulses of electricity. The pulses of electricity are changed into pulses of light in this light-emitting diode. For the receiver, I'll get rid of the selenium photodetector that Bell used, and in its place, I'll put a much more sophisticated light wave receiver. The photodetector in this light wave receiver is hundreds of times more sensitive than the selenium photodetector. I've turned it on. For the modulating source, this transmitter is connected to a cassette tape player, which I'll turn on. And now for the link between them, we'll use this plastic light guide. I'll connect one end to a hole drilled into the light emitting diode, and the other end goes over here to the receiver. And you see the system works. I'll disconnect this end, and you can see how sensitive this system is. Well, it works very well. So as we have seen today, the investigation of light in all its aspects has occupied the interest of Bell Systems scientists and engineers even before the official beginnings of Bell Laboratories over 50 years ago. Today we took a look at some of these areas, and I hope we had some fun in the process. But most important, we've seen that advancements like light wave communications couldn't happen in isolation. It takes the combined efforts of all these Bell System partners to make a modern, efficient light wave communication system possible. The vital partnership, consisting of AT&T, Bell Laboratories, Western Electric, Long Lines, and your local Bell System telephone company, working together to help you to hear the light. Thank you very much.